Welcome to this coding problem walkthrough. In this video, we will tackle LeetCode problem number 892, surface area of 3D shapes. We'll explore the problem statement, analyze different approaches, and break down the solution step by step. Let's dive right in. The problem asks us to calculate the total surface area of a 3D shape formed by stacking unit cubes in a grid. Each cell in the grid contains a number that represents how many cubes are stacked at that position. To determine the surface area, we consider all the faces of each cube that are visible. Each cube has 6 faces, but any face that is adjacent to another cube within the grid does not contribute to the surface area because it is hidden. The task is to write a function that takes this grid as input and returns the total surface area of the 3D shape formed by these stacks. The grid itself is a 2D integer array, where each element represents the number of cubes at a specific position. If a cell contains 0, it simply means there are no cubes there. The output of the function will be a single integer, which is the total surface area. Let's explore examples to better understand the calculations involved. In the first example, the input grid is a 1 by 1 grid with the value 2, meaning there are 2 cubes stacked in a single position. To calculate the surface area, we consider the top and bottom faces of the stack, which contribute 1 face each. Then, for the side faces, the top cube has 4 exposed sides. The bottom cube also has 4 sides, but one of these is shared with the top cube, so only 3 of its sides are visible. Adding these together, we get 1 for the top face, 1 for the bottom face, 4 for the top cube sides, and 3 for the bottom cube sides, giving a total of 10. This is the surface area of the 3D shape represented by this grid. In the second example, the grid is a 2 by 2 grid with different heights at each position. Specifically, the values are 1, 2, 3, and 4. To calculate the surface area, we look at each cell individually. The cell at 0, 0 has 1 cube, contributing 6 faces. At 0, 1, there are 2 cubes, which contribute 10 faces, 6 from the first cube and 4 from the second. Similarly, at 1, 0, 3 cubes contribute 14 faces, and at 1, 1, 4 cubes contribute 18 faces. So far, we have calculated the surface area of each stack as if they were isolated. However, the total will need adjustment for shared faces between adjacent stacks. When calculating the total surface area, we must account for the shared faces between adjacent stacks. For example, the stack at 0, 0 is adjacent to the stack at 0, 1 and they share 2 faces. Similarly, the stacks at 0, 1 and 1, 1 share 2 faces, as do the stacks at 1, 0 and 1, 1 and the stacks at 0, 0 and 1, 0. Each pair of adjacent stacks reduces the total surface area by 2 faces per shared side. Subtracting these shared faces from the initial sum, we get 6 plus 10 plus 14 plus 18 to 2 to 2 2, which equals 34. This is the total surface area of the 3D shape for this grid. In the third example, the grid is a 2 by 2 layout with stacks at diagonal positions. The values are 1 and 2, and the stacks are at 0, 0, and 1, 1. For the stack at 0, 0, we have 1 cube contributing 6 faces. For the stack at 1, 1, there are 2 cubes, contributing 10 faces, 6 for the first cube and 4 for the second. Since there are no adjacent stacks, there are no shared faces to subtract. Therefore, the total surface area is simply 6 plus 10, which equals 16. This example highlights how the absence of adjacent stacks simplifies the calculation, as there are no adjustments for shared faces. The constraints of the problem ensure that the grid size and cube counts are manageable for computation. The grid is always square, with dimensions ranging from 1 by 1 to 50 by 50. Each cell contains a non-negative integer, with a maximum value of 50 cubes. It's important to handle edge cases efficiently. For instance, a single cube at grid equals 1 has a surface area of 6, as all faces are exposed. A flat grid with no cubes has a surface area of 0. For taller stacks, such as grid equals 50, the shared faces between cubes in the same column must be subtracted correctly. By carefully considering these cases and constraints, we can ensure our function handles all inputs accurately and efficiently. When tackling this problem, a brute force approach is a natural starting point. The idea here is to calculate the surface area of each cube one at a time, taking into account its 6 individual faces. To do this, we consider the top and bottom faces, which are always visible if the cube exists, and then analyze the 4 side faces by comparing the cube's height with the heights of its neighbors in the grid. If a neighboring cube is shorter or doesn't exist, we add the difference in height to the total surface area. This method ensures that overlapping areas between adjacent cubes are subtracted, as those faces are hidden from view. The implementation is straightforward, requiring a nested loop to iterate through the grid and simple conditional checks for each neighbor. While the time complexity is O(n) squared, due to the grid traversal, the space complexity is O(1), since no extra memory is needed. The simplicity of this approach makes it effective for handling boundary cubes and zero-height cells naturally, though it can involve some redundant calculations for larger grids. To improve upon the brute force approach, we can apply an optimized method that minimizes redundant calculations. Here, the key insight is to recognize that overlapping faces are limited to adjacent cubes, and we can directly calculate only the visible portions of the surface area. Instead of recalculating everything for each cube, we compute the surface area contributions by focusing on the height differences between neighbors. For each cube, we still add 2 units for the top and bottom faces if the height is greater than 0. Then, for the vertical faces, we compare the current cube's height with its neighbors and add the difference, ensuring that no negative values are included. This approach processes each cube and its neighbors once, maintaining the same O(n) squared time complexity as the brute force method but with fewer redundant operations. It doesn't require additional space, keeping the space complexity at O(1). While slightly more complex to implement, this method is faster for larger grids and aligns well with the problem's constraints. An alternative approach involves pre-computing the contributions of each cube to the surface area of its neighbors. This strategy aims to eliminate redundancy by calculating neighbor overlaps in advance and using these pre-computed values to determine the total surface area in a single pass. First, we create a helper grid to store the contributions of each cube to its adjacent cells. Then we traverse the grid, calculating and storing these contributions for each cube based on its height. Finally, we sum up the total surface area using the pre-computed values. Though this approach reduces redundant calculations in the surface area computation, it introduces an additional O(n) squared space complexity due to the extra grid. The time complexity remains O(n) squared, as the grid is traversed multiple times. This method is most beneficial for very large grids where processing time is critical, but it may not be practical in scenarios with limited memory. The strategy we chose for solving this problem is the brute force approach with minor optimizations. This method is computationally efficient with a time complexity of O(n) squared, and avoids unnecessary complexity, making it straightforward to implement. While the pre-computing approach offers slight performance benefits for extremely large grids, its increased memory usage isn't justified given the typical constraints of this problem, such as n being less than or equal to 50. One of the key insights that shaped our approach was recognizing that the surface area is significantly influenced by how adjacent cubes overlap. By focusing on the differences in height between neighbors, we can simplify the calculations without missing edge cases. Boundary cells and zero-height cells are naturally handled in this approach, as out-of-bound neighbors can be treated as having a height of 0. This simplicity and robustness make the brute force approach well suited for the problem. We chose the brute force approach with optimizations over the alternatives due to its balance of efficiency, simplicity, and scalability. It avoids the overhead of additional data structures, making the implementation clear and reducing the likelihood of errors. While the optimized approach slightly reduces redundant calculations, the difference in performance is negligible for small n, and the brute force method is easier to understand and debug. On the other hand, the pre-computing approach, though faster for extremely large grids, introduces significant memory overhead due to the helper grid, which makes it less practical for typical problem constraints. In summary, the chosen approach delivers an efficient solution while remaining accessible and straightforward to implement, making it the best fit for this problem. To solve this problem, we need to calculate the total visible surface area of a 3D structure represented as a grid of integers. Each cell in the grid corresponds to a stack of cubes, where the height of the stack is given by the value at that cell. Each cube in the stack has 6 faces, but when cubes are adjacent, the overlapping faces between neighboring stacks reduce the total surface area. The input is a 2D grid where each value is a non-negative integer representing the height of a stack, and the output is a single integer representing the total surface area of the entire structure. To compute this, we can use a brute force approach, iterating through each cell in the grid. For each stack, we calculate its initial surface area, then subtract the overlapping areas with neighboring stacks to avoid double counting. Finally, we sum up the contributions from all stacks to get the total surface area. Let's dive deeper into the detailed steps of this approach. We start by initializing a variable, total_surface_area, to 0. To simplify the traversal of neighboring cells, we define the directions for the top, bottom, left, and right neighbors as an array 0, 1, 0, -1, 1, 0, -1, 0. This makes it easy to check adjacent cells without repetitive code. Next, we iterate through each cell, I, j, in the grid. For each cell, we calculate the surface area contributed by its stack of cubes. Each cube in the stack has 6 faces, so the initial surface area is 6 * grid, I, j. We then subtract the overlapping areas for each of the 4 neighbors. For each neighbor, if it is within bounds of the grid, we subtract the minimum of the current cell's height and the neighbor's height, as this represents the shared face between the 2 stacks. If the neighbor is out of bounds, the side is fully exposed and contributes its full area to the surface total. Additionally, each stack contributes 2 units of surface area for its top and bottom faces, which we add separately. Finally, we handle edge cases, such as a single-cell grid, where there are no neighbors, and an empty grid, where the surface area is simply 0. For edge cells, we ensure that the algorithm correctly accounts for boundaries where some neighbors do not exist. These outer faces remain fully exposed and contribute their full area to the total surface. After processing all cells in the grid, we return the total_surface_area as the result. This approach effectively calculates the surface area by iterating over each cell and adjusting for overlaps with neighbors. Subtracting overlapping faces is crucial because adjacent stacks share faces, and these overlaps should not be double counted. For boundary cells, where neighbors are missing, the outer faces are fully exposed and need to be included in the total. The computational complexity of this algorithm is O, n*m, where n and m are the dimensions of the grid. We iterate through all cells, and for each cell, we check up to 4 neighbors. While this is efficient for small grids, we could explore optimizations, such as pre-computing boundaries or using a 3D grid representation, to simplify neighbor checks further. However, the current method is both straightforward and efficient for the problem as described. The algorithm leverages simple data structures for clarity and efficiency. The input grid is represented as a 2D list, which allows easy access to cells and their neighbors using index-based traversal. To simplify neighbor calculations, we use a predefined list of directional offsets. This reduces code duplication and makes the logic for checking adjacent cells more concise. Let's walk through an example to see how the algorithm works in practice. Consider the grid 1, 2, 3, 4. For the first cell, 0, 0, with a height of 1, we compute its initial surface area as 6 * 1 = 6. Next, we check its neighbors. To the right, the neighbor, 0, 1, has a height of 2, so the overlap is min, 1, 2, = 1. Below, the neighbor, 1, 0, has a height of 3, so the overlap is min, 1, 3, = 1. Adding the top and bottom faces, we calculate the total contribution for this cell as 6, 1, 1 + 2 = 6. This process is repeated for all other cells in the grid, adjusting for overlaps with neighbors and accounting for top and bottom faces. For the next cell, 0, 1, which has a height of 2, the initial surface area is 6 * 2 = 12. Checking its neighbors, the left cell, 0, 0, has an overlap of min, 2, 1 = 1, and the bottom neighbor, 1, 1, has an overlap of min, 2, 4 = 2. Adding the top and bottom faces, the total contribution for this cell becomes 12, 1, 2 + 2 = 11. Similarly, we calculate the surface area for each remaining cell, adjusting for overlaps and including the contributions from top and bottom faces. After processing all cells in the grid, the total surface area for this example grid is 34. This step-by-step process ensures that we accurately calculate the visible surface area while avoiding double-counting overlaps. By iterating over all cells and handling edges and boundaries appropriately, the algorithm provides the correct result efficiently. This solution calculates the surface area of 3D shapes represented as a grid. The surface area function iterates through each cell in the grid. If the cell's value, height, is greater than 0, it performs the following calculations. 1. Adds the top and bottom faces, 2 units of area. 2. Computes the side faces while accounting for overlaps. For the north, up, direction, subtract the height of the northern neighbor, if it exists. Similarly, calculate overlaps for south, west, and east neighbors. If there is no neighbor in a direction, the entire face is added to the total area. These calculations are performed for each cell in the grid. Finally, the function returns the accumulated surface area. Here, we have the Java implementation of the solution to calculate the surface area of 3D shapes represented on a grid. First, we define the method surface area that takes a 2D grid as input. The variable n is assigned the grid's length, which gives us the dimensions of the grid. We also initialize total area to 0, which will accumulate the total surface area. Next, we use 2 nested loops to iterate over each cell in the grid, representing a specific column of cubes. For any cell with a non-zero height, we start by adding the top and bottom faces, which contribute a fixed area of 2. Then, we calculate the visible surface area of the north face. If the current cell is not in the first row, we subtract the height of the cube in the row above from the current cell's height and add the result if it's positive. Otherwise, if it's the first row, the entire height of the cube contributes to the north face. This same logic is applied to the south face, where we check the row below, and similarly to the west and east faces, where we check the left and right columns, respectively. If there are no neighboring cells in the respective direction, the entire height of the current cell contributes to the face in that direction. Finally, after finishing the nested loops and processing all the cells, we return total area, which now holds the complete surface area of the 3D shapes. This implementation ensures that we account for all visible faces while avoiding double counting where cubes are adjacent. The logic is efficient, as it processes each cube in constant time, resulting in an overall time complexity of n squared, where n is the grid size. To begin solving the problem, we start with a very simple example, a single cube. The input grid is a 1 by 1 matrix with a single value of 1, meaning there's one cube at position 0, 0. First, we initialize the total surface area, total_area, to 0. Now, for the single cube, we add the areas of its top and bottom faces, which contribute 2 units to the total area. Next, since there are no adjacent cubes in any direction, north, south, east, or west, all 4 side faces are exposed. This adds 4 more units. Summing these contributions, the total surface area becomes 6. Thus, for this single cube, the output is 6. Now, let's consider a slightly more complex case, 2 adjacent cubes arranged horizontally. The input grid is a 1 by 2 matrix, where the values indicate cube heights. At position 0, 0, the height is 1. We add 2 for the top and bottom faces and 4 for the side faces. Since there are no adjacent cubes to the north, south, or west, all these sides remain exposed, and the total area at this point is 6. Moving to position 0, 1, the height is 2. Again, we add 2 for its top and bottom faces. For the side faces, we account for overlaps. The west side overlaps with the cube at 0, 0, reducing the exposed area. Specifically, the overlap is equal to the smaller of the 2 cube heights, which is 1. We subtract this overlap and add the remaining exposed sides. The updated total surface area becomes 13. Thus, the final output for this grid is 13. Finally, let's examine an example with cubes stacked vertically. The input grid is a 2 by 1 matrix, where the first row has a height of 1 and the second row has a height of 2. At position 0, 0, the height is 1. We add 2 for the top and bottom faces. For the side faces, the north, west, and east sides are fully exposed, contributing 3 units, while the south side overlaps with the cube below. Since the overlap covers the entire height of the top cube, we don't add any area for the south face. This gives a total area of 6 so far. At position 1, 0, the height is 2. Again, we add 2 for the top and bottom faces. For the sides, the south face, as well as the west and east faces, are exposed, but the north face overlaps with the cube above. The overlap reduces the exposed area by 1 unit, leaving 2 units for the north side. Adding these contributions, the total surface area becomes 10. Therefore, the output for this grid is 10. To analyze the time complexity of the algorithm, we start by considering the nxn 2D grid, where n represents the size of the grid. The algorithm processes each cell in the grid using a nested loop. The outer loop, referred to as the I loop, iterates over each row of the grid, running exactly n times. For each iteration of the outer loop, the inner loop, or J loop, iterates over each column in that row, also running n times. Within these loops, the algorithm performs a constant amount of work for each cell. Specifically, it checks whether the value of grid I, j, is greater than 0, adds 2 to account for the top and bottom faces of the 3D shape, and calculates additional contributions for the north, south, west, and east faces. All of these operations are simple comparisons and arithmetic, each taking 1 time. Since these constant time operations are performed for all n*n cells in the grid, the total time complexity of the algorithm is n squared. The time complexity remains consistent across all scenarios, best, average, and worst cases, because the algorithm always processes all n-2 cells in the grid, regardless of the grid's contents. This ensures that the time complexity is n squared in every case. Now, turning to space complexity, the algorithm uses memory for the input grid, which is an n*n matrix. However, since this is provided as input, it doesn't count as extra space. The auxiliary space used by the algorithm includes a few variables, an integer total underscore area to keep track of the surface area, 2 loop control variables I and j, and some temporary variables for intermediate calculations. All of these require constant space, meaning the additional space usage does not grow with the size of the grid. As a result, the total space complexity is 1, since no additional data structures are used and the memory requirement remains fixed, regardless of the grid size. When comparing the optimized approach with a brute force method, the differences become clear. A brute force approach would involve explicitly constructing the 3D shape by stacking cubes according to the grid values. Calculating the surface area would then require iterating over all the surfaces of this 3D structure. This process would use additional memory proportional to the number of cubes in the 3D shape, which could reach n cubed in the worst case. Furthermore, the time complexity for calculating the surface area in this scenario would also be n cubed, due to the large number of surfaces to process. In contrast, the optimized algorithm bypasses the need to construct the 3D shape entirely. Instead, it directly computes the surface area from the 2D grid, reducing the time complexity to n squared, and the space complexity to 1. This optimization is made possible by processing each cell in the grid exactly once, with constant work per cell, as demonstrated by the mathematical proof of the algorithm's big O complexity. To summarize, the algorithm achieves a time complexity of n squared, and a space complexity of 1. This efficiency stems from the fact that it directly calculates the surface area without constructing the 3D shape, ensuring that both time and space usage remain minimal. Compared to the brute force method, the optimized approach is significantly more efficient, especially for larger grids, as it avoids the overhead of additional memory usage and unnecessary computations. This makes the algorithm well-suited for handling grids of any size while maintaining optimal performance. When solving this problem, there are a few common pitfalls to watch out for. First, overlooking edge cases can be a big issue. For example, if you forget to handle single cubes, disconnected components, or edge cubes that don't share all sides, your surface area calculations will be incorrect. This happens because these special cases often have more visible faces than fully surrounded cubes. Another mistake is double counting overlapping faces. If you subtract overlapping areas multiple times when iterating through adjacent cubes, you'll end up underestimating the total surface area. Incorrect iteration over the grid is another common issue. If you only iterate in one direction, such as rows but not columns, or accidentally skip certain neighbors, you'll miss some adjacent cubes, which leads to incorrect visibility calculations. Finally, there's the inefficiency of brute force implementations. If you recalculate overlapping faces for every pair of cubes, even after they've already been processed, you can end up with very high time complexity. This can be especially problematic for large grids, where such solutions may even time out. Now, another mistake to avoid is assuming uniform input. If you assume all cubes are connected or that the input is always well formed, you might miss edge cases like negative values or improperly validated data, leading to runtime errors. From an interviewing perspective, this problem is often used to test your ability to recognize patterns and break down geometric challenges. For instance, calculating visible faces per cube requires you to understand spatial relationships in 3D grids. Efficient solutions often involve processing neighbors only once to avoid redundant calculations. Techniques like BFS or DFS for connected components are popular strategies here. Additionally, handling edge cases, such as single cubes, hollow spaces, or irregular grids, is a key part of demonstrating thoroughness. Interviewers also appreciate when candidates can discuss trade-offs, such as between time and space complexity, comparing an O(n) optimized solution to a more naive O(n) cubed, brute force method, for example. Finally, visualization is a powerful tool. Drawing quick sketches to clarify your logic not only helps you stay organized but also leaves a strong impression of your structured thinking. This problem also connects to other related challenges, which can help deepen your understanding. For example, LeetCode 695, Max Area of Island, explores connected components in a 2D grid using BFS or DFS, while LeetCode 463, Island Perimeter, involves calculating visible edges in a 2D grid, which is conceptually similar to this problem. LeetCode 200, Number of Islands, focuses on adjacency and connected components in grids, and LeetCode 1245, Tree Diameter, although not directly about grids, deals with spatial relationships in graph traversal, which can provide useful insights. Beyond related problems, alternative approaches to this challenge can also enhance your problem-solving repertoire. For instance, optimized iteration involves calculating the surface area contribution as you traverse the grid in a single pass. This approach reduces time complexity to O(n), but it requires careful tracking of visited nodes to avoid errors. Another method is using the union-find data structure to group adjacent cubes and calculate the surface area for each group. While this approach simplifies adjacency calculations, it tends to be more memory-intensive, so it's important to weigh the trade-offs. Additionally, BFS and DFS are excellent strategies for tackling connected components in this problem. By traversing the grid incrementally, you can calculate surface area step by step. This method is often more intuitive, especially for visualizing how cubes connect, but it may have higher runtime for particularly large grids or sparse data. Regardless of the approach you choose, the key is to balance clarity and efficiency while addressing edge cases thoroughly. This combination of skills not only ensures correct results but also demonstrates the depth of your understanding during an interview. Great job following along. To recap, we discussed the brute force approach for calculating the surface area of 3D shapes and analyzed its complexity. We hope this helped reinforce your problem-solving skills. Thanks for watching, and be sure to like, subscribe, and check out our other videos. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!